I'll try that. Okie dokie. So yeah, welcome everyone to week 12, last weekly meeting. Thank you for sticking around, and thank you to the people on YouTube watching this later on, or the day before exams, whenever you happen to be watching this. So today we have, again, pretty content-like compared to some of the more heavy ones during the term, during the semester, but we still have some interesting micro topics for you, antibiotics and antivirals and stuff. And then we'll be going on to a bit of the other stuff, so medicine of the mind, HEP, and HKS. So I'll hand it off to Deepak to take it away.
Yep. So as James said, we're going to be starting with some microbio. So we got some, pharmacology. And so we got antibiotics, antivirals, antifungals. So this is stuff you guys covered in week 11. Unfortunately, the slides weren't available back then because I hadn't done it yet, but now it's here. So I'm going to use this rather like a resource for you guys to tap into for just like nice tables to revise with. And I'll go through some of the more key points. So we'll be running through the pharmacology part, unless people have questions, in which case drop it in chat. But let's get started. All right, so there are these 11 antibiotics that you should know at this stage from these lectures, or from this lecture in particular. And we'll be going through each one of them and how they're categorized. Also, big thanks to PS Pingu and PS Papa for the slides from last year. And going into it, so what is an antibiotic? So essentially, it's just the use of a chemical to control or treat a disease. And we call that chemotherapy. So it's not just cancer treatment that's always conventionally chemotherapy, but antibiotics is a form of chemotherapy too. And it can be used in a couple of different ways. So we've got directed, empirical, and prophylactic use. So directed is when we know the pathogen's identity due to culture results available. Empirical, essentially, we just don't know we don't have the proven pathogen. So we might roughly know what it could be based on the probability in terms of prevalence and stuff, but we just haven't gotten the investigation results back. And prophylaxis is essentially just used for prevention. So if you go to some disease endemic country like dengue, then you want malaria prophylaxis. So antibiotics administration, there's a lot of different stuff that you should understand about it. So antibiotics fall into roughly two categories. So that's bacteriostatic and bactericidal. So bacteriostatic would inhibit or slow the growth of the pathogen, while bactericidal would actually kill the pathogen. And this means that in bacteriostatic infections, your body's immune system needs to work to actually kill off the pathogen, because it's not going to kill it, it's just going to stop the growth. And the way through which it might do that is, for example, interfering with protein synthesis. Bactericidal, it might kill it, but at the same time, it can have an effect where the dying bacteria releases toxins that is actually toxic to surrounding bacteria. So it's like a carpet bomb, it just bombs the region, which is pretty useful for us. And an example would be interfering with the cell wall. In terms of dosage and the concentrations in the body, there's three different markers we're looking at. So there's minimum inhibitory concentration. So that's the minimum concentration for a bacteriostatic effect. And there's the minimum bactericidal concentration. And there's a minimum effective concentration for desired outcome. So MEC could either be MIC or MBC. So it kind of suggests that the activity of the antibiotic can change depending on the concentration. So at low concentrations, it seems to have a bacteriostatic effect, and at high, it seems to have a bactericidal effect. I imagine, or my understanding of this is that the bacteriostatic effect is just the number of bacteria has stopped increasing because we're killing it at the same rate as it's replicating at. And bactericidal is just when the concentration is high, so we manage to decrease the bacterial numbers. So there's another antibiotic effect. So that's the prolonged growth suppression after antibiotic levels drop below MEC. So when over time, as our body metabolizes the antibiotic, it drops below the minimum effective concentration that we technically need, but there is still prolonged bacterial growth suppression. So this means that we can actually, if we take that into account, we don't need to give our dosage that frequent. And that reduces risk of adverse effects and also things like bacterial resistance, the development of resistance and stuff like that. All right, so more on dosage. So drugs can typically work in two different ways. So they can either be time dependent or concentration dependent. So time dependent means that they have the best effect for as long as the concentration is above the minimum effective concentration. So what this means is all we need to do is just to keep the drug above the MEC for as long as possible. And the goal would be probably about at least 60% of the dosing interval. On the other hand, we have concentration dependent. So that's an increasing effect of increasing concentration. So we just want to maximize the concentration of the drug, but keep it under toxic levels because we obviously don't want to harm the body. And the antimicrobial creed is basically it's like a guideline of 6 different things that we need to consider for providing the most, I guess, ethical or the most effective antibiotic treatment. So first of all, it's acronymized as MIND-ME, and MS, microbiology guides therapy, indications are evidence-based, and you need drugs that have the narrowest of spectrums. Dosage is individualized and appropriate to site and type of infection. You want to minimize duration of therapy and ensure oral therapy where clinically appropriate, because it's the least invasive type of therapy. I just had a question in chat. Antibiotics classified as either bactericidal or bacteriostatic, or bacterial based on what they target. So typically they're based on what they target, but you just need to know what bacteriostatic and bactericidal really means. But yeah, we're going to go into the method of action, which is what they target, and that's exactly how we're going to categorize antibiotics. So that's a good question because it leads right into the slide where you can see that antibiotics essentially impact different steps of the bacterial replication cycle. So we've got cell wall synthesis, folate synthesis. So folate is just a precursor. It's one of the ingredients that you need to produce nucleic acid. And then below that, we have nucleic acid synthesis and we have protein synthesis. And underneath all those headings are all the different types of drugs that we have. And I'm just going to relate it back to this slide. So we're going to come back to this probably. So starting off, let's have a look at folate synthesis. So we've got sulfonamides and sulfones and DHFR inhibitors. Let's have a look at what they actually are. So it's just pictures taken from the slides. So on the left, this is just the pathway for the formation of folate. So it comes from para-aminobenzoic acid, which is a precursor to folate. And sulfonamides and sulfones just target the enzymes for folate synthesis or creation of folate. So that's pretty straightforward. So if you stop that, folate's not going to form, DNA is not going to form. You inhibiting replication. Again, on the right, we have, again, another type of folate inhibitor. But in this case, this is after the formation of folate, before the formation of DNA. So this is an enzyme called dihydrofolate reductase, which is used to convert DHF to THF. And the inhibitor would be a dihydrofolase reductase inhibitor, for example, trimethoprim. Wait, just to follow up to the question in chat. Yeah, from my understanding, yeah, you can allocate them, but that wasn't really I don't think that was necessarily the scope of what we need to know, but I'm sure you can allocate them. I'll look into it after I'm done with my stuff, and I might even check up a slide for that. But for now, folate synthesis. So going back to DHF reductase inhibitors. So our example is trimethoprim. And you just ignore the first sentence here. But our example is trimethoprim. The other one is sulfonamide. We don't need to know the example of the drug here. And here's just the method of action and some more information if you need. Okay, so going to cell wall synthesis, targeting cell wall synthesis. So we have beta-lactams, glycopeptides, and tuberculosis drugs. TB drugs can, there's a bunch that overlaps with other stuff, but cell wall synthesis of tuberculosis. I mean, the cell wall of tuberculosis is pretty unique, and that's something that you need to know. But we have a couple of different drugs. So when we say beta-lactam, we call it that simply because the antibiotic that is considered a beta-lactam has a beta-lactam ring in the molecular structure. So it's just a structural thing, right? And you have two different types. You have a penicillin and cephalosporins. So beta-lactam penicillin, an example is amoxicillin. Beta-lactam cephalosporin, example is cephalexin. For amoxicillin, the way it works, or for both of them, both beta-lactams work by irreversibly inhibiting the transpeptidase enzyme, which is an enzyme needed in cell wall synthesis. Amoxicillin is typically first line, cephalexin is second line. Again, a bit more info on the right. In terms of toxicity, cephalexin is neurotoxicity. Since we're targeting the transpeptidase, it's generally more effective for gram-positive because they're going to have a peptidoglycan layer that is thicker than gram-negative bacteria. So that's something that it makes sense when you look at why we treat certain bacteria with certain drugs. For vancomycin, that's a glycopeptide, which is the other type that we talked about, and it irreversibly inhibits the transglycosidase enzyme. And this is only used for gram-positive. And typically it's used for more severe infections that is resistant to methicillin. I mean, to methicillin, which is stuff like the beta-lactams. So it's used for methicillin-resistant Staph aureus, and then methicillin-resistant, another one, can't remember exactly. And something that it has is red man syndrome if it's administered too fast. And alongside nephrotoxicity and ototoxicity. So nephrotoxicity is toxicity of the kidneys. Ototoxicity is toxicity of the ears. I just had a question. Are drugs always either bacteriostatic or bactericidal, or do they change their effect depending on concentration? From the mode of action, it makes sense for them to be either bacteriostatic or bactericidal. But we know that, I mean, from like this slide, this diagram suggests that the effect changes based on concentration. So yeah, I'll answer that later, or I'll come back to that later. That's a good question. All right, so the next target is going to be nucleic acid synthesis. So we're going to be two different things. So here's like a diagram, which is a good introduction to it. So this is just a screenshot or like a screen cap of the process of unwinding of the DNA as it primes itself for protein synthesis. So at the top here, you have DNA gyrase, which is an enzyme necessary for unwinding, also known as topoisomerase 2. And ciprofloxacin is a type of fluoroquinolone, which also inhibits CPI4. But the main thing is that this is the way that it works. Metronidazole is another one which basically interacts with the DNA to form an unstable intermediate product, which inhibits DNA replication. So these are the two ones. A bit more info. So ciprofloxacin is more broad spectrum, while metronidazole is specifically for anaerobic stuff most of the time. So that's like Giardia and other parasitic infections. Also, stuff in italics are like memory tools or ways to remember, which have been pretty useful and passed on from generations of PSPs. But yeah, that's more info if you wish to have a look at that. So the next one is protein synthesis. All right, so protein synthesis, what do we talk about? There's three different ones, which is macrolides, aminoglycosides, and tetracyclines. And we can categorize them to roughly the 50S or the 30S part of the ribosome. So the ribosome is composed of two different parts, right? And we can interfere either of those parts in different manners to have a different effect. So macrolides, they bind reversibly to the 50S, which interferes with movement of the ribosome along the mRNA. And some more info on the side effects there. Aminoglycosides irreversibly bind to 30S. So, and that's specifically for gram-negative as well, and can cause misreading of mRNA. Tetracyclines reversibly bind to 30S, and this interferes with tRNA binding to mRNA, so formation of the ribosomal complex. Also, for any info that you think should be in the scope of, or if you're trying to figure out what's in the scope of what you need to know, have a look at the ePharmacology website, which is always useful because since that's the benchmark for what we need to know by the end of year one, or by the end of our preclinical years. All right, so TB antibiotics. So, okay, so tuberculosis has a pretty unique structure with a mycolic acid layer, and we have different drugs specifically for that. So the acronym that we use is RIP, right? Which is rifampicin, isoniazid, pyrazinamide, ethambutol. So rifampicin inhibits RNA polymerase. Something specific, like a lot of them are hepatotoxic, so that's something you can remember. And also rifampicin has some orange, it turns your secretions orangey red. Isoniazid inhibits mycolic acid synthesis, so that's one of the parts of the cell wall specific to tuberculosis. And that was antibiotics. But yeah, we are kind of running through it since this is meant to be content delivered last week. And also, I think it doesn't really help if I read off the slides. So if you guys have any questions, any more questions, chuck it in chat. Thanks, James, for answering. But I'll move on to antivirals. Okay, so viruses can be classified into a bunch of different, in a bunch of different ways. So we can have DNA viruses and RNA viruses, and within DNA viruses, we can have single-stranded DNA or double-stranded DNA. RNA, we can have single-stranded RNA or double-stranded RNA. And there's a bunch of different viruses under each of those classifications. And we can have viruses that convert RNA to DNA through reverse transcriptase. And a famous one for that is HIV, which is a retroviral, retrovirus. On the right, we can see the typical life cycle of a virus and ways in which we can block it. So we're going to refer back to that diagram as we go through our classifications, or like the categories for drugs. Just a bit more info though. So most viral infections are self-limiting. So we don't actually need antivirals for the most part, unless this host is immunocompromised. And we'll get to that in a second. So there's also no real broad spectrum antiviral since it's very specific to viral specific proteins. And one last thing is all available drugs are virus static, meaning it's not going to kill the virus. So host immunocompetence is very important, which is again why most viral infections are self-limiting, except for people who are immunocompromised, and also in high-risk populations like pregnant people, neonates, and elderly. And these antivirals can only affect the replicating forms. So, for example, there are a lot of latent drugs, latent viral infections. So chickenpox can become latent as shingles in the dorsal root ganglion, and it cannot be affected when dormant. And since we're talking about latent stuff, here's a list of key viruses that go latent. So we have herpes simplex virus types 1 and 2, such as the common herpes. So that's type 1 would be oral cold sores, and type 2 would be genital sores. And it hides in the DRG, which is the dorsal root ganglion in your spinal cord. Again, and also in salivary glands for type 1 specifically. We have Epstein-Barr virus, so that's glandular fever or infectious mononucleosis, which is another name for it. Another type of herpes virus. So you'll see that in brackets we have herpes virus. It's just the family or the classification of it. Epstein-Barr lives in lymph tissue, and it's also salivary glands, also specifically called kissing disease. So that's that. Varicella zoster, we know that as chickenpox, and it goes latent as shingles, as we talked about just then, latent in the DRG as well. And due to immunosuppression, it becomes prominent or flares up. HIV lives in lymphocytes and macrophages. Yep. Again, so it's just this diagram again. So we're going to start with nucleoside analogs. So nucleoside analogs, we're looking at acyclovir, which is on the right here. So you can see that, which is the fourth line down on this diagram on the right. And that they're essentially targeting nucleic acid synthesis. So the way it inhibits the DNA synthesis is by being a analog for guanine and essentially just incorporating into the DNA, which results in chain termination. So it just messes up the DNA sequence. Used for varicella zoster, herpes simplex, and some side effects of malaise, GI, and headache. Also, when I say in brackets shingles, that is that's for like the version of varicella when it re-emerges as shingles. The next one would be the neuraminidase inhibitor. So going back to this, so we've got this one over here in the bottom left, which is essentially blocking viral release from packaging and assembly. So that's, yeah. So a bit of context about neuraminidase is that influenza, so we hear stuff like H1N1. So what that really means is the influenza, which contains two different proteins are involved in it, or enzymes, I should say. So hemagglutinin and neuraminidase. The H stands for hemagglutinin and stands for neuraminidase. That's essentially it. And then as the number changes, that's suggestive of antigenic shift. So the example here is oseltamivir or Tamiflu. Inhibits neuraminidase, which is a glycoprotein, which cleaves viruses from the cell surface for release, used in influenza A and B, and in prophylaxis as well, and has GI disturbances, so you should take it with food. Okay, so the final part of antivirals, which is pretty important, is HIV. So we're going to talk about a bunch of HIV drugs, but before then, a bit of context. So the aim of HIV treatment or antiretroviral therapy is not cure, since we can't fully cure HIV, since we can only target it when it's replicating and always goes latent and stuff. So we can have periods of remission, but ultimately we're searching for maximal suppression, so that's less than 50 RNA copies per milliliter. We want to restore immune function, since HIV is a virus that causes immunosuppression through AIDS. We want to resolve symptoms and improve quality of life. We want to reduce mortality and transmission. So in order to monitor our success, it's generally done through CD4 plus count. So CD4 is a type of uh, immune cell, and viral load, which is essentially the number of viruses, which is going back to the less than 50 RNA copies per milliliter. A bunch of principles of treatment as well. So we want combination therapy. So that's 3 or more drugs from 2 or more classes, and we can combine that into a pill to reduce pill burden, improve compliance. Since if we ask people to take a bunch of pills, that it isn't very helpful in terms of compliance because it provides more opportunities to make mistakes and a bunch of other reasons as well. But the adverse effect rate is also very high compared to other drugs. So this will probably impact compliance. So we need to balance our treatment based on what the patient wants as well, and can tolerate. But if compliance is bad, it can lead to multi-drug resistance, which is pretty bad. Treatment should be individualized. So going back to what I was talking about, so we want to balance the compliance with the potency and the toxicity to find something that actually works for the patient. So we have a couple of drugs. We have a protease inhibitor. So protease is an enzyme which cleaves proteins. And this works by inhibiting late protein synthesis and processing. You can see it in the bottom right here. So late protein synthesis and processing blocked by protease protease inhibitors. And this one key thing about this is that it's a pharmacoenhancer. So if we have this drug, it boosts the levels of other protease inhibitors for some reason. So this means that we can reduce dosing frequency for those drugs while raising the barrier to drug-resistant virus variants, since we don't need that much dosage to kill off the viruses anymore, which is very useful for us. But there's a ton of side effects, as we talked about, since HIV drugs have a ton of side effects. Probably keep in mind specifically the first 3 dot points. So that's drug interactions, GI, and hepatotoxicity, but you can have an array of different complications or adverse effects, sorry. So the next one would be a nucleotide reverse transcriptase inhibitor. And in this case, we can combine the next 2 drugs. So that's a combination of tenofovir and emtricitabine. I think the commercial name is Truvada, but the way in which it works is by blocking reverse transcriptase. So we talked about how HIV is a specific virus that converts RNA to DNA, and it does it through reverse transcriptase, and by blocking it, we prevent transcription and replication. Used for prophylaxis as well, and used for combination therapy. The last one is the last drug, which don't really fit in a category, but something that's kind of important, is interferon alpha. So interferon alpha is actually an endogenously produced cytokine protein. So we call it kind of like a biological drug, since it's technically not synthetically produced, in the sense that it's not unnatural or whatever. But essentially, it just stimulates the immune response interface of viral RNA, and it's used for Hep B and C and some cancers. Okay, so onto the final part, antifungals. So this was attached on to the end of our antivirals lecture for us, and we only have 2 specific antifungals we're going to talk about. Before we get to that, some context. So something about antifungal treatment is that the patient should have a systemic fungal issue before commencing treatment, because if we're going to give systemic treatment, we want to have the best effect about it, and we don't want to just give it to treat something that is more localized, since antifungals always have serious effects when taken systematically. So that's just some clinical relevance. So they must have a systemic issue before systemic treatment. And also, same thing as viruses, we have fairly narrow spectrum limited drugs. We can also still break it down exactly like how we broke it down for the other 2. So we can target different things DNA synthesis, cell division, the cell wall, cell membrane. But yeah, here's essentially a list of different ways that we can kill fungal cells. So we talked about cell membrane disruption. So that's the drugs that we're going to go through. So the things bolded are the ones specifically that you should know. So ergosterol is a type of sterol, which is essentially the cholesterol of fungi membranes, and fungi cannot survive without it. So this means that by inhibiting the creation of it, we can kill fungi. And we have things like glucan synthesis inhibitors, nucleic acid inhibitors, antimitotic. So that's stopping spindle formation. But specifically, I want you guys to just focus on the first two. Also, you might come across the word chitin, chitin, which is a unique polysaccharide found specifically in fungal cell walls as well. Just some info. So I just had a question. Do we need to memorize the modes of action for all these medicines? Is it okay to just memorize the different classes of medications and their modes of action? So it's best to categorize it into classes since they typically have a similar mode of action, but I think you should know most of these modes of actions. Yeah. James, can you give your 2 cents on that as well?
So the question, okay, memorize modes of action for all this medicine, different classes of medications, modes of actions. Yeah, so it's sort of the same thing, because ultimately most, oh, sorry, okay, so within each like class, I assume by class you mean like the different like broad categories. We have different levels of organization. So we have antibiotics, antivirals, and antifungals. And then within those, we have a number of different things. So you might have penicillins in antibiotics, you might also have cephalosporins, that sort of thing. So within each of those categories, say most penicillins work pretty much the same way. Most cephalosporins work pretty much the same way. And I don't think that there are many cases where you have like a lot of drugs from one category on your core drug list. So in practice, what you do is you will end up looking at the mode of action of each of those categories. So you say, okay, penicillins do this, and then that should be more than enough. Because if you, as long as you're able to link a drug, if they give you on the exam, you know, a multiple choice question, if they give you a drug, and you're able to link that drug back to a category, and then from there get the mode of action, side effects, things like that, then you should be fine.
Thanks. I hope that was helpful. So moving on to back to antifungals and stuff. So again, these are just the two that we need: amphotericin B and fluconazole. Amphotericin B, on this diagram, we can see that it is a cell membrane disruptor. And the way in which it does this is by binding to ergosterol, forming amphotericin B pores. So basically punching holes in the membrane, in the cell membrane, which changes the cell permeability, causing movement of substances in and out, essentially leading to an environment which is unsustainable for life and cell death. And the class is a polyene antifungal, that's what we call it. Drug of choice out into the bloodstream, Candida and Aspergillus. And we got nephrotoxicity, which is kidney toxicity, fever, chills, and vomiting as side effects. The azoles, fluconazole, so this diagram again, ergosterol synthesis. So it messes up the fungus-specific cytochrome P450, which is necessary for cell membrane synthesis, and it essentially breaks it. Generally, it's better tolerated than the other one, but still has cytochrome P450 interactions and GI disturbances. Okay. So that's the end of pharmacology stuff. Just remember that one other question I just need to get to, but I'll get to that later. But we're moving on to medicine of the mind, or psych, which is pain. So thinking about pain. So definition, unpleasant sensation that signals injury. So it's something that has the purpose. It needs to signal injury, right? And pain is felt in a couple of different ways. So there's the idea of a pain threshold or a pain tolerance. So a threshold is when a stimulus essentially becomes painful. So you can imagine yourself poking yourself until it becomes unpleasant to something that's actually painful. This threshold is similar for most people, but tolerance is what varies between individuals, and that's the degree to which the degree to which how painful it is. So if you were to rate it on a scale of 0 to 10, people might rate it differently based on the pain tolerance, but people won't say it's not painful at all because they would have passed the pain threshold. So going to types of pain, it's categorized into mechanism and duration. So mechanism is nociceptive and pathological. So nociceptive is noxious stimuli activating nociceptors. So this is it's a very neurological thing. So you stubbing your toe activates nociceptors, causes pain. Pathological, by that we mean it's more of a abnormality, some disease process that causes pain in the actual nerves and in the pain mechanisms themselves. So for example, diabetes causes peripheral neuropathy, which damages nerves, which causes pain, which is distinct to the normal action of nerves firing due to noxious stimuli. Duration, so we've got acute and chronic. Acute generally subsides of healing less than 6 months. So 6 months is always going to be the cutoff period for acute versus chronic. And for treatment of that, we focus on fixing it. Chronic, usually it's not life-threatening, but could be lifelong and is greater than 6 months. And for this, we want to focus on coping since we cannot be fixed, usually. You can go into remission, but cannot be fixed. So you want to focus on more psychological stuff, the meaning of the pain and stuff like that. So we can understand pain in 2 different ways. I want you guys to understand gate control theory pretty well, since that's generally what we see more questions on. But we have 2 different models. We have the biomedical model and the gate control theory. So the biomedical model is something that we know. It's kind of just the nociceptive mechanism. So that's just stimulation of nerves causes pain. Pain severity is proportional to tissue damage as well. So those are 2 key things. Gate control theory, on the other hand, understands pain as a perception influenced through your higher processes such as thoughts and emotions. And we see pain as manipulated by gates or stopped by gates. So gates can open and close, and they open and close in response to different things. So for example, pain fiber activity opens the gate for pain. Activity from other sensory nerves, however, closes the gate for pain. So for example, if you rub your toe after stubbing it, it actually decreases the subjective pain you experience, despite still actually having the same amount of stimulation, but we have more input that are brain processes, which takes away from the pain, so we're not as focused on it. And finally, the key thing is that we have a higher processing center, that is the brain, that can influence the pain. So if you're distracted from the pain and you're in a good and positive frame of mind, it closes the gates more. If you're focused on the pain and you're in a bad and negative frame of mind, then it opens the gates. The advantage for a gate control theory over a biomedical model is that we can account for different situations. So injury without pain, so that's a closed gate. Pain without injury, it would be messages from the brain. It's explained by messages from the brain, like the phantom limb, for example. So the next one is the placebo effect. So this is essentially explained by the gate control theory. So essentially what the placebo is a mimic that lacks the active ingredients of the drug. So the sensory input that you get is exactly as you would for the drug. So it's undistinguishable, but it just doesn't have the same effect. And when we give someone a placebo after the given active treatment, we see that they have continued benefits and continued side effects of the initial drug. So the reason why is ultimately due to perception of the drug, and it's due to input from your brain, which is in theme with the gate control theory model. So for example, we know that your beliefs impact the perception of your pain. And in this case, this is, in the case of a placebo, we see two different effects that we see two different effects. And one of them is classical conditioning. So you just went through conditioning and stuff earlier. So classical conditioning is essentially when the drug becomes coupled with the alleviation of the symptoms. So taking something that mimics the drug still alleviates the symptoms. The expectancy effects. So we see what we expect to happen. So it's kind of like a confirmation bias due to a learned behavior. So that is, those are the two key mechanisms through which placebo works. And it kind of teaches us a little bit about how the brain is so important and effective, and pain can be influenced by the brain. That's just what I was trying to say. The other one, so we talked about classical just then. Operant condition is also relevant in this context, but in a different manner. So it's kind of not super related, but operant conditioning is to do with more of the reinforcement of pain behaviors. So for example, expression of the pain. So if you grimace or if you yell out in pain, it results in attention and care, which could be a desired outcome for an individual. So the more the care and attention they're getting, the more positive reinforcement they have for pain behaviors. So yeah, that's that. So management of pain. There's a lot of different aspects to management of pain. In terms of education, we have patient education, physician education. So patients is to address fears of things like addiction tolerance, especially when you're giving pharmacological treatments of opioids and things like that. Physicians is more to keep up to date with new info, fix misconceptions. For like medical management, we have pharmacological stuff like analgesics, surgical stuff like anesthetics, and for cancer pain, we have radiological interventions. So for physical stuff, we have a bunch of different things like yoga, exercise, relaxation techniques, which the way through which it works is usually by alleviating anxieties and directly impacting the messages from the brain. So that's kind of like a distraction away from the brain, closing the gates. Psychological, so this is the key one. For chronic pain, as we talked about earlier, we have cognitive behavioral therapy, where we focus on things like adaptive coping strategies, correcting maladaptive ones, increasing self-efficacy, reducing pain and distress, and things like that. And that concludes medicine of the mind. So drop any questions if you guys have. But I'll hand it off to someone for pharmaceutical industry.
Yep, that's me. Give me 1 second, I'll bring it up. All right, you're all able to see that? Awesome.
Yes.
Okie dokie, let's start with that. So the pharmaceutical industry, so you guys have probably heard big pharma and that sort of thing. That's sort of what we're covering here. Having a look at how drug companies work the world over, and sort of the implications upon healthcare, of how our system is set up at present. So basically, we need to think about how do we actually get drugs into the hands of patients. So like we sort of take it for granted, especially in developed countries like Australia, that there are medicines available, and that they're relatively easy to access. So, you write a script for a patient and they're able to go to their pharmacist or whatnot and get it. But there's a lot that goes into that behind the scenes. And especially when we look at other countries, which is a sort of, you notice this is a sort of running theme in EdgeCast, we like to look at other countries which aren't quite as fortunate, and see how they, how the same things which are very easy to do in our countries can often be quite hard there, because they lack the infrastructure, the development, all sorts of things which are needed to do it. So we need to think about basically what are the things that need to happen for drugs to get to patients. So the first thing is that they need to exist in the first place, which seems like a bit of a no-brainer, but which is an important consideration. So a lot of diseases just don't have treatments. So we might have a partial treatment or a prophylactic treatment, but no actual treatment once once the disease takes hold. There's a lot of gaps in our pharmaceutical coverage. And so if you want to treat a patient with a drug, the drug needs to exist in the first place. So how do we get new drugs? Well, we need to do research and development. So that means both research in our sense, so the clinical sense or laboratory research to try and test new drugs, and also continual development in not only in actually testing the drug itself, so clinical trials, that sort of thing, but also in developing manufacturing techniques for the drug. So there's a lot that goes into actually turning it from a experimental treatment into an actual commercial one. So we have two terms here that we use. So one is medicines. So medicines are the actual drugs, like the pills, the chemicals, all sorts of things. Diagnostics are the investigations that we use in clinical practice, basically. So something like urinalysis, where we have a little strip with certain chemicals which help us diagnose different diseases, which detect substances within the urine, which then help us diagnose. That would be considered a diagnostic. And those are all sort of under the same umbrella because they're both made by pharmaceutical companies. All right. We also have regulatory approval. So in Australia, the Therapeutic Goods Association is the one that regulates what pharmaceuticals are allowed to be sold in Australia. So obviously all your pharmacies, all of your hospitals, they're all going to be looking at the TGA for approval in order to make sure the drugs that they're using are safe. So that can be a problem sometimes, needing to have that approval. It can be a bit of an extra hurdle when it comes to approving certain drugs, especially if we have a new experimental treatment which is promising, and in certain developing countries which have under-resourced regulatory bodies. So if you're in Gabon or whatnot, and your health regulatory body has very little money, very little ability to do actual trials, that sort of thing, then it could be years while it's tied up waiting for approval. Of course, in Australia, where we have a bit more resources, we can usually do that faster. At the same time, it's important that we do have at least some check there. So not all just government bureaucracy. It's also important that we remember there are consequences for letting unsafe drugs get to the market. So the thalidomide scandal you guys might have even learned about in school. And so it's important that we test drugs and that we make sure they're safe before we start actually giving them to our population. All right, affordability, another one which seems sort of obvious, but which is an important thing nevertheless. So what goes into affordability? Well, there's the price of the drug itself. So certain drugs are just easier to manufacture than others, especially the more common drugs. So the more common a drug is, the larger the market it is, the easier it is to scale things up. Whereas a niche treatment, which might only be in demand from a very small number of patients, and which might be very complicated to manufacture, that might be inherently more expensive. But on top of that, we can also have a number of different causes which put the price up even further. So the government can put tariffs if it's coming from overseas. They can put taxes if it's coming domestically. Companies that make the drugs, they can have markups, and in places like the US, those can get quite obscene. And there's also logistical costs. So it's one thing to make a drug and then to pay your taxes to have your markup to make your profit. It's also another thing, apart from just making the drug, you do need to actually get it there logistically, which ties in nicely to our next little thing, which is logistics itself is a challenge. And so we need to get the drug from where it's made. It needs to be stored because it won't always be used immediately. It needs to be able to transport. We need to get it to distributors, so end people who will actually be able to connect it to patients, and then to patients themselves. So this can be really, really complicated. Not every drug used in Australia, and in fact, not even necessarily the majority of drugs used in Australia, will be coming from Australia. And so international trade is a huge element of getting drugs into where they need it, basically, or as we'll find out more, like into where people can pay for them. So this is another thing, which is a major source of discrepancy between, say, developed countries and developing countries, because in many cases, the infrastructure that we have, so it's just sort of taken for granted again, slowly built up over time. We have fairly good roads. We have heavy transport infrastructure. We have ports. We have airports. We have all sorts of things required to transport things. Whereas a country which is, say, in the middle of a conflict or recently out of a conflict or just never had a large degree of governmental wealth might not be able to develop those and will lack existing infrastructure when it comes to trying to get drugs in. And of course, that's already becoming an issue with COVID vaccines in certain cases. All right, so we have two concepts to talk about here. So globalization is a very umbrella term. So that's basically talking about over the past few decades, basically. So this is a process which started, it's been going on since the dawn of time, but it's accelerated massively in the past few centuries, and especially since, say, 1940, 1950 onwards. And this is basically just increasing contact between countries, so trade, communication, cultural exchange, all sorts of things, even immigration. And this is sort of talking about increasing global connectedness. We've also got another topic here, another concept here, which is the idea of neoliberalism. And this is the academic sense of the word. So this is like talking about like Reagan and Thatcher, their sort of ideology. And that was the driving force for globalization as pursued by a lot of international institutions like the World Trade Organization and the OECD. And so since they followed that philosophy to varying degrees, we can see the impact of those upon global trade and global pharmaceutical industry practices. So basically, the priorities there are you privatize things. So it's based on the idea that private endeavors are generally more efficient than government endeavors. Deregulation. So again, if private stuff is more efficient, then why would you have barriers to it? And the removal of barriers to trade, so free trade essentially. And again, you want to limit government interference because the assumption is that the market will provide more or less. So proponents of this, and so it's hard to disentangle these two things because again, especially in regards to the West as opposed to development, which has been mostly spurred by countries like, say, China or the USSR back when that was a thing. In Western globalization, these sort of philosophies have held true and have influenced things. So proponents of both things will point to the fact that we've increased earnings globally, we've increased health indicators. So if you look over there at the side, you can see how global life expectancies in pretty much every country have risen over the past century or so. But we also have critics of the process who point out that there's increasing health disparity between countries, and so the benefits aren't actually shared equally necessarily, and we also have issues with exploitation and whatnot. All right, so the fables, the infamous big pharma. So this is basically talking about either we mean large pharmaceutical companies, or we mean pharmaceutical companies in general. And so obviously you'll mostly hear it be used as a scare quote, and so that connotation basically belies a whole bunch of different concerns people have about the pharmaceutical industry. So several of these are quite relevant for HKS purposes. So one of the most important ones is basically if your pharmaceutical development is driven by profit motive, then you're not going to go for drugs that necessarily maximize health benefit. You're going to go for drugs which will maximize your profits. And so what ends up happening in a lot of cases is that a rich country with a lot of cases of, say, a fairly minor disease will receive a lot more funding and a lot more research than a poor country with a lot of cases of a significant disease. And so the health burden is objectively higher in several like low-income countries, essentially, but they don't get as much attention. And part of that is the profit motive. Part of that is also because research facilities, researchers, and research funding is concentrated in those high-income countries. And so we see an overall inefficient health system or pharmaceutical development system because we're focusing on largely developed countries, which are able to pay for drugs, basically. We have a specific case study, which is called neglected tropical diseases. You'll hear these a fair bit when we're talking about things like population health and public health in general. And so this is a specific group of diseases which are quite impactful. So there are huge numbers of people who have these diseases, and they're quite severe diseases, but they have almost no research focused on them compared to, again, relatively milder conditions in Western countries, which have more research. And that's why we call them neglected, because they're not being really afforded the interest in the research which their impact in the world would suggest. Again, high drug prices. So if you have a profit motive, you're also, to a degree, especially if you have a patent, which we'll get into, you are incentivized to raise the price of your drugs in order to maximize your profits. There's also the issue of patents in general. So there are positive, negative effects, and there are also effects which can be positive or negative depending on your outlook. So a patent, if you guys don't know, it's basically something that says, I invented this, so I'm the only one who gets to make it or decide who else can make it for the next 20 years, basically. So the reason we talk about 20 years is because it's the international standard under the UN's TRIPS agreement, which you will probably be learning about. And so basically, the cornerstone of a patent is that you are the only one allowed to make something if you invent it. So the positive side of this, and the main justification for patents, is the idea that if you put a lot of time and money into researching a drug, then you want to make sure that you get some sort of return from that, especially if you're a pharmaceutical company. So governments are able to just sort of fund things for the public good because they get their funding from a completely different source, i.e. taxes. But for companies, the money that they put into R&D has to come from somewhere. And so as a company with a desire to maximize their profit, they're going to invest in things that they think will give them back more profit. And so this sort of incentivizes them to put that money into research and gives them some sort of security in that investment. On the other hand, the fact that they're the only ones who can produce that for 20 years can also lead to the possibility of a monopoly. So if nobody is able to make other versions of the drug which do the same thing, then you're basically controlling the pricing for that entire mode of treatment. And that can lead to massively jacked up prices and whatnot. And so in certain cases, there are very cheap generic versions of drugs available. That doesn't always mean that it's a good solution. So in the case of things like insulin, we have mainline treatments, which are made by big pharmaceutical companies and often quite expensive. And those are going to use the latest technology. They'll be continually taking out patents as they sort of slowly improve it. And then the generic drugs will lag a significant distance behind, and they'll be cheaper, but they won't be as good. And at the same time, because of those patents, we can also have issues where we basically end up having drugs which are okay prices for developed countries, but which are far too high for developing countries. So ARVs are antiretrovirals, which basically are specifically important for things like HIV, so retroviruses. And so South Africa had an epidemic of HIV and is still, to a degree, having an epidemic of HIV. And they need a lot of antiretrovirals, but the prices were basically too high for the government to acquire in bulk. And so they had to resort to trying to import generic versions, and they actually got dinged because the TRIPS agreement is meant to prevent people circumventing it like that. So you can see there a case where patent law is obviously in pretty direct opposition to getting the maximum Medicare to people in need. Right, that pretty much wraps up the pharmaceutical industry. I'll hand it over to Kyle for connectedness.
Yeah, I'll take a moment and share screen. Second to make sure nothing crashes. Well, it is crashing. That's good. Oh. All right. I'm not sure if you can hear me. Can you hear me, James?
I can hear you and I can see you. You're lagging a little bit. Your share is moving very slowly. Has your computer frozen? Nope.
I might ask you to screen
no,
share and
easy
I'll
peasy.
just talk through it. Sorry.
Yeah, it's like 4 slides.
Sorry about that.
Easy peasy. No worries, man.
Oh,
One
my
second.
computer hates education.
Right,
Yeah, so connectedness, what is it? So if we go to the next slide. So connectedness is a sense of belonging to or having affinity with other people. So feeling like you're connected to other people. And it can have pretty profound impacts on your mental health. So the more connected you are, so that's a legitimate, sincere sensation of that, will actually counteract your stress. Whereas if you have decreased connectedness, so that's also known as isolation, then you're going to have some pretty profound impacts on your health. So the likelihood of you becoming ill and the severity or rapidness with which your illness progresses will actually increase. And so that's pretty straightforward in things you think, for instance, with depression, but also it extends to other examples such as chronic pain, infections, and just general overall immunity. A key distinction here is the distinction between isolation and solitude. So isolation is the bad one. Solitude is the not necessarily bad one. The way I sort of think about it is like Superman's headquarters or his safe place was his fortress of solitude, I'm pretty sure. And so that wasn't a bad place for Superman to be. Anyway, isolation is basically when you're feeling excluded from the community or feeling emotionally removed from social connections. So you're not feeling connected. A lot of the time, this can be involuntary. And a really key statistic is the fact that this isolation actually doubles mortality rates. So your likelihood of dying is doubled by you being isolated. In contrast, solitude is when one chooses to remove themselves from being around others. So introverts unite, and it's not a determinant of poor health. It actually can be particularly healthy. Yeah, you feel, so you're physically isolated, but you feel connected. That was actually sort of a key thing in discussing of social versus physical distancing, the linguistics of that. In staying safe with COVID-19, that actually saying physical distancing is better than saying social distancing, because social distancing might imply to stay away from people in terms of don't have relationships, don't talk to people over the phone or interact with them in a safe way. And that would result in isolation, which is quite evidently bad. All right, next slide, please, James. Yeah, so other impacts of isolation. So it results in generally decreased social support. Because of this, you're not sort of exercising those social muscles. So your social communication skills are sort of reduced. Your engagement in day-to-day activities and things like that are reduced. Same with job opportunities and your access to health information, because you're not being social as much. And so for all of those things, we can see that these are negative impacts. On top of that, this specifically other health impacts. So we have a change in genetic profiling. So that sort of ties to development. So if you were more nurtured as a child, generally, then that increases the amount of serotonin that you produced, which is a happy neurotransmitter. And that would in turn affect your cortisol levels, resulting in a reduction of your risk of being stressed, or your likelihood of being stressed. On top of that, just more general psychological impacts. So as we were tying back to the depression and things like that, and your experience of pain, you're more stress prone if you're isolated, and your immunity is reduced as well. And that sort of ties into having shorter telomeres. Just a note with that genetic profiling thing, that was obviously an example of not being isolated, of having good connectedness with your parents. Whereas if you did not have any parents or guardians sort of nurturing you, then obviously that increases your risk of stress. All right, next slide, please, Jim. All right, so tying into development and connectedness. So adolescents that were raised, so teens that were raised in sort of harsh, negative environments, that resulted in overstimulation of an area in the brain called the amygdala, and underdevelopment of the prefrontal cortex, which is involved in emotion processing. And so this resulted in these people being predisposed to being more antisocial later in life. And this is sort of similar to the correlation that teens with issues with aggression, so particularly young men, they have larger and more reactive amygdalas, and the prefrontal cortex is reduced, the development of that. On the other hand, positive and supportive parenting styles, those resulted in healthy brain changes, particularly, once again, amygdala and prefrontal cortex. So the increase in amygdala is sort of a detriment to your emotional health, and an underdevelopment of your prefrontal cortex is the same. Okay, with mindfulness, though, you can actually counteract this, so you can result in positive brain changes. So quietening the amygdala and improving memory and learning. And there's some pretty decent evidence behind this, I'm pretty sure. And I think the final slide, please, James, or the second last slide, very briefly, very important. But racial discrimination, so it strongly influences mental and emotional health of racial minority groups in any community. And a specific quote is that interpersonal experience of racial discrimination and the internalization of negative racial bias operate jointly to accelerate biological aging. So that was actually a US study found by measuring telomere length in African-American men, that telomere shortening happened at a faster rate in African-American men, I'm presuming independent of other factors. So yeah, very important. And the final slide, please, James, I think. Yeah. So how can you be connected? Generally by being around people and having relationships. So that's through marriage. Although obviously if you're in an unhappy marriage, then you're not going to be feeling very connected. Relationships with families and friends, especially in adolescence, it's a good protective factor against certain health risk behaviors. Religious affiliation, but tying back into my spirituality topic last week, that would need to be an intrinsic religious orientation. If you had an extrinsic religious orientation, then you're probably not going to be feeling like you're actually believing in the religion. You're probably not going to be feeling genuine, and so you're probably not going to be feeling connected to other people of the same faith. Interactions with professionals, so psychologists are great way to feel more connected, and to help with anything mental health related, general group associations, and technology. Relevantly, social media can obviously have a very negative effect. You can feel it can actually contribute to isolation. However, if you're actually using it to increase your social interaction in a generally healthy, positive way, then that makes you more connected, which improves your well-being. And I think that's it for this week. So if you have any questions, feel free to ask. But yeah, it's pretty straightforward. A lot of the medicine of the mind sort of stuff. As long as you sort of figure out, okay, this is the thing that is good and this is the thing that is bad, you can sort of logic through a lot of it. And it's relatively low yield.
Yeah, we had a question in chat. So this is about HEP in particular. So like how to study for it, how is it examined. HEP is a bit different to other subjects in general. So in practice, the HEP questions on your exam are like going to be like 6 questions and they're mostly recycled from previous years. So I definitely wouldn't recommend sinking a lot of your time into trying to memorize like the 15 million statistics that get put out every lecture. It is a very good thing to try and get the concepts involved in HEP. So some of the stuff that we've talked about, like the different general strokes and the general ideas, because those will help guide you in your answer. But there are also going to be like a whole bunch of questions which are just a few major statistics that they've decided are important, and so they end up using on exams. So like there's one on the Mediterranean diet that keeps popping back up. There's another one on, I think, something about cancer risk. So there are a few of those that just sort of circle back periodically. Like I said, the main thing, don't like bash your head against the wall and just revise on HEP. It probably won't bear fruit if you try and do, every single statistic. And it's just really hard to remember. So I'd suggest do your past exams, have a look at those, focus on those, and understand the broad strokes.
Yeah, I was just going to say very briefly, a PSP last year created like a few sheets that had HKS, HEP, and medicine of the mind, like key concepts and key statistics. I've been making sure to include what they say in those in our slides as well. But if you want sort of the concentrated original source, then I think that's a great place to go. I've chucked the link in the chat. But for those who are watching, if you look at the week 12 slides, under the sort of title slide for Connectedness, I have PS Pain Relief 2020. Otherwise, just message me and I'll check it up, or I'll put it in the Facebook group. But that's a great place to go because it's really concise and has all of those key statistics that James was mentioning as well.
Yeah. Right, I think we'll formally wrap it up there. So feel free to stick around if you have any other particular questions. But overall, thank you so much for having me today. Thank you so much for sticking around through the semester. I know it's difficult to get up 10 a.m. on Monday and come listen to this, but obviously you guys seem to get something out of it. And to you guys online as well, thanks for watching. So yeah, thank you so much, and we'll see you next semester.
Good luck for exams. Don't stress too much.
Yeah,
you've got this. Just
you
put
guys
in
are
a little bit
amazing.
more work, but you'll be great. All right.
Thank you.
Lots of love.